We will discuss condition for no tension, right? Since we know that machinery or column designed for taking compressive load is not capable of taking tension, right? So we have to ensure that no phase of these structures develops tension to avoid failure due to cracking, right? And this limits the eccentricity E to a certain value, right? To a certain value, which we will discuss here, right? So objective of this analysis is to make a calculation for a limit of eccentricity, that is E, right? Clear? Because value of this is E will give you a zone, right? Zone in which if we apply compressive stresses, then there will be no tension across the section, and outside this zone when we will apply compressive stresses, there will be the chances that tensile stresses will be generated in the section, right? So in previous lecture we concluded that for no reverse stresses there are two possible cases, right? When sigma d is greater than sigma b or equal to sigma b, right, then there will be no tensile stresses in the section. So sigma b we know that is equal to m upon I into y. M is equal to W into E, where is the eccentricity, right? This load is eccentric from its center by amount E, right? So W into E, and value of M is W into E, and Y, value of Y we have taken D by 2, because in if column is of circular section, right, then Y will be D by 2, or if column is rectangular cross section, here in this case, and load is applied across across this x-axis, right, here load W is applied, right, at point P, which is on x-axis, and right, and this x-axis is parallel to diameter, parallel to depth of the beam, because this is rectangular cross section, right? So here value of Y for this x-axis will be D by 2, right, D by 2, and if this cross section is circular even again, then this value will be value of Y will be D by 2, right? So for a general I have make a general assumption that in most of the cases when load is applied on x-axis, then Y will be equal to D by 2. So I put up here D by 2, right? Now where load is applied on x-axis, then we will take a moment about y-axis. Be very sure, if load is applied on x-axis, then moment will be taken about MY will be taken about y-axis of that load, right? And if load is on y-axis, then MY will be about x-axis. So here in the problem we will put the value of I directly in the equation. Here I have made it because we are going to generate an inertial formula of eccentricity, which is going to limit it in a certain zone, right? Then I is equal to put I equal to AK square in terms of radius of gyration, right? So expression is now E is less than equal to 2K square by D. This value is saying that when we will apply load W at distance E, then this E must be less than or equal to 2K square by D, right? If we apply load, right, up to this value, then there will be chances of tensile stresses in the section, right? And if we apply load below this value, right, below this value, within this value, then there will be no tension in the section. Clear? Now we will make a calculation for eccentricity, for the limit of eccentricity, right, in case of rectangular cross section and circular cross section. When we calculate limit of eccentricity for rectangular cross section, so this method is also known as middle third rule, right? Middle third rule. Here I have made plan of given column section. plan of given column section. Here this is my column that we have considered, and plan is top view of this column. Top view will be A, B, C, D, and load is acting at point B. When we will make a plan, then there will be no line of load, right? Because it will be seen at point P. Here I made it, right? This is A, B, C, D is our plan, and here load is acting at this point. Clear? Load is acting at this point, right? And it is a distance C from the centroid. This is depth D and this is bit P. This is our x-axis and this is y-axis. Load is on x-axis, right? When load is on x-axis, then MY will be taken about y-axis. Be very clear. When load is on x-axis, so for this case, this MY will be considered. IYY equal to for this case, so for this case, IYY will be considered right here, BD cube by 12, right? It is different from normal situation, right? In normal situation, when we make a rectangular cross section, then here will be width and here will be depth, right? So be very clear that when we were going to solve a problem regarding combined bending and direct stresses for a column structure, and we are making a cross section, rectangular cross section of a column, then this horizontal position will show the depth of the column, and this vertical line will show the width of the column rectangular cross section, right? And then MOE, because load is acting at this point, when we take a moment, then this moment will be about y-axis, about this y-axis, right? So IYY is BD cube by 12. So when load is on an x-axis, right? Load is on an x-axis, then MOI will be taken about y-axis. Be very clear of it. Clear? So now about this diagram, we will discuss this diagram at the end of the result of this discussion, right? So see, when load W is placed on x-axis, right, positive side means here load is, right, this is our load, this load is on positive side, right? This is origin O, this is the positive x-axis, right, and this will be negative x-axis. So load is on positive x-axis, right, at distance C. Clear? So when load is on when load W is placed on x-axis, that is on positive side, then sigma D, for condition of no tension, right, sigma D is greater than or equal to sigma B. Clear? And put the value M into Y, right? And this is IYY. What I have said earlier, that when we will take when load is placed on an axis, then we will take MY about y-axis, right? This is IYY. Now y will be equal to dy by 2. This is our y, right? This is the top fiber, and distance of this centroid, right? Position of this top fiber will be d by 2, right? This total is d. Then this is our y, right? For this case, this is our y. There should be no doubt on it. Clear? So y is dy by 2, IYY will be BD cube by 12, right? Simplify this equation. When we will simplify it, then what we finding? Ex, right? Here because load is on an x-axis and E is measured on x-axis, then this is Ex, right? Then Ex is less than equal to dy by 6. And similarly, when W will be placed on negative x-axis, right here on this side, here at this position, right, and will be distance at E, the same situation will go out here, and Ex will be less than equal to dy by 6 for that calculation also, right? What is the conclusion, right, coming out from this result? Clear? The conclusion coming out from this result, that this we see that here I have written it very correctly, that no reverse stresses occurs when load is placed at a distance not more than d by 6 on either side of the centroid on x-axis, right? Clear? There will be no here, right? This is our d by 6 and this is our d by 6, right? So it is saying that no reverse stresses occurs when load is placed at a distance not more than d by 6 here, not more than d by 6 on either side of centroid. This is our centroid point. This distance is d by 6 and this distance is d by 6, right? When load is placed on these distances, there will be no tension in the section for all these section, right? When load is placed in between this distance d by 6 will be d by 3. So when load is placed between these d by 3 of the section, then there will be no tension all over the section, all over the face of the column, right? Then this is the conclusion, right, of this analysis. So what we can say, that limit of eccentricity is equal to d by 6 plus d by 6, that is twice of ex is d by 3, right? Here I have made it clear that this is equal to twice of ex on x-axis and this is equal to d by 3. So we have 2 points on x-axis, one is here and another is here, right? These 2 points are barrier, right? Barrier for what? Barrier for putting a compressor load on x-axis, right? If we put our compressor load beyond this barrier, there will be chances of tension in the section, right? When we put our direct load in between these points, then there will be no tension all over the face of this section, right? So this is the conclusion from this result. Now similarly, when if load is placed on y-axis, right? Here it is point P, so this is it, here it is placed on this point and this is point over Q. Clear? So what will be the result? Yeah, I made it. When load W is placed on y-axis, right? Here at point Q, load is placed on at point Q, right? At this point, load is placed on at point Q at this point. Then moment we will take about x-axis, right? About x-axis. Clear? Here moment of this load will be taken about this x-axis. Then when load is placed on y-axis, then my will be moment of inertia will be taken about x-axis, right? So for condition of no reverse stresses or no tension, sigma d is greater than equal to sigma b, right? And m into y upon ixx, right? Here y will be equal to, this is our y, right? Y will be equal to b by 2, because this y load is placed on y-axis, then distance of top 5 from this centroid will be equal to y max and this is equal to b by 2, and this because this dimension is equal to b, right? Then put this value here, y is equal to b by 2, ixx will be db cube by 12, right? Area is bd. Clear? And put this value because it is measured, E is measured on y-axis, so I made it EY. So EY will be less than equal to B by 6, right? So and if W is placed on negative y-axis, right? Here, say this is Q dash point, right? So answer will be same for this condition. So these are the 2 points, right? These are the 2 points here. This distance is y equal to B by 6. And this distance is equal to b by 6, right? The same result will be there. Then what will be the conclusion? Conclusion is no reverse stresses occurs when load is applied at a distance not more than b by 6 on either side of the centroid on y axis, right? So we have found 4 points, right? We have found 4 points. When load is placed on x-axis, 2 points are found, and when load is placed on y-axis, these 2 points are found, right? When we make them by join them with a straight line, a rhombus will be formed, right? A rhombus will be formed, right? This this closed area is also known as kernel, right? Sometimes it is also known as kernel, right? Then length of this kernel along x-axis is equal to dy 3, and on y-axis it is equal to by 3, right? So we can see a generalized statement is made right here. What is the generalized statement from this conclusion, right? This is equal to b by 3, twice of a equal to b by 3. Generalized statement will come that if the load is placed anywhere inside this rhombus, right? If the load is placed anywhere inside this rhombus, then the reverse stress will not occur in any part of the entire rectangular section, right? It is saying that if the load is placed, right, anywhere inside this rhombus, then there will be no tension all over the section, right? And if load is outside of this rhombus, right, if load is placed at here or it is placed at here, then there will be tension in the section. But if load is placed between this zone, right, then there will be no tension in the section. Clear? Then there will be no tension in the section. So because the this rhombus lies in between middle third of this area, middle third of this dimension B and D, so it is also known as middle third rule, right? It is also known as middle third rule. Clear? So in case of rectangular section, do remember that a rhombus is formed and dimension of rhombus is d by 3 and b by 3, that is middle third of the section, and rhombus is formed at the middle third of the section. When load is placed inside the rhombus, there will be no tension. When load is placed outside the rhombus, there will be tension in the section, right? This is the condition for no tension in rectangular cross section. Now we will discuss condition for no tension in circular cross section, which is also known as middle fourth. Now be very clear. In case of middle third, there are middle third of the section. In case of here middle fourth rule, if it is known as middle fourth rule, so there will be middle fourth of the section, right, where we will apply load, then there will be no tension in the section, and when we will apply load outside the middle fourth of the section, there will be tension in the section. Let's see for condition of this is our circular cross section, right, and diameter of this circular cross section says D. Clear? Diameter of the circular cross section is D. Say for condition of no tension, sigma D will be greater than equal to sigma B, put M into y because there is symmetry in the section. XY IXX is equal to IYY, so there is no such a specific attention will be made that where is load is placed on x-axis or y-axis, because IXX is equal to IYY. But in case of rectangular section, be very clear, when load is placed on an x-axis, then MOI will be taken about y-axis, and when load is placed on y-axis, then MOI will be taken about x-axis. But here in case of circular section, there is symmetry in XY, so there is no such a case, there is no such a specific attention is required, right? So put the value I is equal to pi by 64 d to the power 4, y will be equal to d by 2, and when we will simplify, then what we find that Ex will be less than equal to d by 8. Similarly, when we make a calculation for load when placed on y-axis, then Ey will be less than equal to d by 8, right? So limit of eccentricity will be twice of Ex and twice of Vy, and when we make it, then we find that twice of E is equal to dy 4 on both sides. So we can say that diameter of kernel or diameter of this area, right, diameter of this area is equal to dy 4 dy 4, that is the middle fourth of this section, So a statement is made here that there will be no tension in the section when load fall within middle fourth of the section, right? When load fall within middle fourth of the section. That's why this rule is also known as middle fourth rule for condition of no tension in circular cross section, right? So this is all about combined bending and torsion. Now there is I request all of you that make a calculation for eccentricity, limit of eccentricity, right, for hollow rectangular cross section and for hollow circular cross section, right?